Hello, everybody, and welcome back to Geography 340 Climatology. I am Zach Hilgendorf, and in this lecture, we're going to be talking about the composition of the atmosphere. In the last lecture, we talked about structure of the atmosphere. This one, we're going to focus on the gases and particulates that make up the atmosphere. So, first off, let's start with kind of a definition. What is air? We breathe it, it's all around us, but what it really is it? So it's a mixture of a number of discrete gases, each with their own physical properties, and in which varying quantities of tiny solid and liquid particles are suspended. This composition isn't constant. However, if we removed all the particulate matter, water vapor, and other variable components, we'd find it's actually pretty stable and a pretty stable makeup up to about the first 80 kilometers or so of the atmosphere. What about particulates? Well, simply particulates are little liquid droplets and solid particles suspended in air. What is suspension? Well, suspension refers to the process of keeping an object aloft in a fluid. More often, we think the term suspension in terms of suspended load of a river or the suspension of particles in sediment transport by wind. Atmospheric suspension takes the latter concept a step further, where suspension of a particle in a fluid, in this case the fluid is our atmosphere, air, can extend kilometers into the atmosphere. Winds aloft can maintain particle suspension for thousands of kilometers. Dust plumes from transport events in Africa can actually serve as nuclei for storm development in the Atlantic, which can evolve into hurricane activity that impacts the east coast of North and South America. So how can a particle stay up like that? Well, shouldn't it just fall back down to Earth? Yes and no. Particles of that size, for example, dust or much smaller, even smaller particles than that, have a very low terminal velocity. So it's really easy to maintain that suspension aided by rising air parcels. If we recall back in our last lecture, the troposphere is very turbulent. It's very unstable. There's a lot of mixing of air within the troposphere. So that's able to keep those particles suspended. So what are atmospheric particulates? Well, we can see some of them here. They serve as the nuclei for clouds. So liquid and solid particles, such what we call aerosols. Also water droplets and crystals, so condensed or frozen water can serve as nuclei as well, or atmospheric particulates. From more terrestrial sources, sea spray and salt, whatnot can serve as a nuclei. Wildfires can kick off lots of particles into the atmosphere. In that bottom left, that's actually from the Phoenix metropolitan area. That's what we call a haboob, a dust storm. That can send a lot of particles in the atmosphere, volcanoes as well. And those are the natural sources. Then we move into some of the unnatural sources, the contributions that we supply to the atmosphere through rather vast sources of pollution, through industry and through automobiles. So all of these serve to eject things from kind of more the terrestrial sphere into the atmosphere to serve as a composition really of our atmosphere. Some of them natural, some of them unnatural. So we're going to focus on permanent and variable gases and particles throughout the next number of slides here. But first, let's kind of talk about another law. We talked about Newton's second law in the last one. Now we're going to look at the law of the conservation of mass, which simply says that in a chemical reaction, mass is neither created nor destroyed. For example, the carbon atom in coal becomes carbon dioxide when it's burned. The carbon atom changes from a solid structure to a gas, but its mass does not change. So, and the rate of change is the mass input in minus the mass output rate. So basically we're looking at how much is coming in, how much is going out. There's a conservation, so there might be storages or deficits, but mass is always conserved. So the atmosphere is a cloud of gas and suspended solids extending from Earth's surface out many thousands of miles, becoming increasingly thinner with distance, but always held by Earth's gravitational pull. The atmosphere is made up of layers surrounding the Earth that holds the air we breathe, protects us from outer space, and holds moisture, i.e. clouds, gases, and tiny particles. In short, the atmosphere is a protective bubble that we live in. So this bubble consists of several primary gases, with the top four of them making up 99.998% of all gases. Those are nitrogen, N2, oxygen, O2, and argon, and carbon dioxide. We'll get into those here in a little bit. By far the most common is nitrogen. It dilutes oxygen, it prevents rapid burning at the Earth's surface. Living things need it to make proteins. It's transparent, provides heat capacity and momentum. It's exchanged with biomass. It's decomposed in combustion. So we see in the table that we can see here before us. Then oxygen, used by all living things. It's essential for respiration. It's also necessary for combustion and burning. Also provides some heat capacity and momentum. Moving next, we have argon. It's used in light bulbs, but it's also in our atmosphere. It doesn't really serve much of a role, but it is one of those chemicals and one of those gases that is just kind of hanging out and actually making up a rather primary gas, permanent gas in our atmosphere. Then plants use carbon dioxide, moving into the next one, to make oxygen. It also acts as a blanket and prevents the escape of heat into outer space. It also absorbs infrared light, contributing to global warming. Not necessarily the best outcome. And it is a product of combustion. So now moving into some of our variable gases. Start off with water vapor. It absorbs infrared light, contributes to global warming. Also, it exchanges with liquid and solid forms, exchanges with life. We need it. And it is also a product of combustion. Where does water vapor in the atmosphere come from? Where does it go? Well, these are some of the primary sources. Condensation and evaporation. So evaporation from our major water bodies, or really anywhere that there is water standing on the surface or running on the surface, there is an exchange between the air and the water. So there's evaporation of the water on the surface. And transpiration is the other. We think of our rainforests as kind of the lungs of Earth, right? Well, they're exhaling this water vapor. They're evapotranspiring this water vapor from their leaves and other sources that, as they grow and as they exchange energy. Next, carbon dioxide. We've kind of touched on that before. That is exchanged through decomposition of organic matter or cellular respiration, whether that's through plants. That's another byproduct of that lungs of Earth is carbon dioxide and oxygen exchange between plants. We also emit carbon dioxide as a byproduct of our respiration. Comes from other sources as well. Carbon is released into the atmosphere through volcanic activity, through wildfires and burning, and also just through exchanges with the oceans as well. And through things like agriculture. So all of these things together make up the carbon cycle, which we can kind of see illustrated here. So there's a natural exchange of carbon through organic decomposition, through the intake of carbon dioxide by plants, through cellular respiration, and through our oceans as well. And then we add a pretty hefty amount to it as well through burning for industry and through transportation and other human activities. And then we hinder that cycle by doing things like clear cutting our rainforests. We're removing those carbon sinks, injecting essentially more into the active atmosphere. And through poor forestry practices as well, these expansive wildfires, you can see that image in the top right, also contribute to releasing carbon into our atmosphere. So we can kind of see here that exchange between fossil fuels, vegetation, soils, wetlands, rivers, the ocean, and other organic material, humans. All of these things serve as kind of a their own little piece in this global carbon cycle. So through natural means, you have this carbon cycle of, like I said, things decomposing, being released back into the atmosphere, being taken up for use by vegetation, being stored in places like wetlands and rivers in the ocean. But then there's that carbon or that constant cycle of material. So as it decomposes, uh, and remember, conservation of mass, it can't be uh, really destroyed. That mass has to go somewhere, and it might be going into our atmospheres, and it is going into our atmospheres, as we'll see here pretty soon. So first off, I'm going to ask, who has heard of this gentleman? Charles Keeling, uh, very famous scientist. We'll see here in just a couple slides, if you're not familiar, and that arrow in the bottom left there, that's pointing to Hawaii, to the Big Island. On the observatory on the Big Island, ringing a bell yet? The very top of Mauna Loa, there is a NOAA observatory. And what does that do? It is Earth Systems Research Laboratory's Global Monitoring Division. If you're not familiar, if you've never heard of Charles Keeling, he developed something called the Keeling curve. What is the Keeling curve? Well, this might start to look a little bit more familiar. It is the atmospheric carbon dioxide observed at the Mauna Loa Observatory. The Keeling curve is a measurement of the concentration of carbon dioxide in the atmosphere made atop Hawaii's Mauna Loa, which is a big shield volcano, since 1958. It is the longest running such measurement in the world. And this, in a lot of ways, is looked at as kind of the smoking gun for anthropogenically driven climate change. We can see here, this is the rise in CO2 from 1958 through into 2002. This was grabbed the beginning of September of 2022. Pardon me, I misspoke earlier. And this is basically what we're looking at here is we've seen a rapid increase in carbon dioxide at this observatory and at other locations in the world, all having to do with industry and with the change in really the composition of our atmosphere and the composition of our planet through anthropogenic sources. So we'll talk a little bit more about the Keeling curve and about methane and their relationships here in just a few slides. But this is something that I'll provide some resources for to go look at yourself in the description below the video here, and some links to go check things out and learn more about this. But for now, let's go ahead and talk about methane, or CH4. So it absorbs infrared, it exchanges with life, all these other things that a lot of these other gases do as well. They're byproducts of organic matter on the planet. Methane can be given off by anaerobic decomposition, which we can see here. So methane oxidizes into H2O, water, and carbon dioxide, CO2. Ruminants, so organisms with multi-chambered stomachs, like cattle, for example, deer, elk, kind of your other quadruped ruminants, all, I guess, contribute to this anaerobic decomposition. You can see termites here as well. Wetlands also contribute to this, but then, surprise, surprise, we do too. Through agriculture, large animal feeding operations, or cattle feeding operations, CAFOs as they're often called, rice growing and other agricultural sources, just row crop agriculture as well, a little bit. Extraction contributed through extraction, open pit mining, and oil and gas extraction. Landfills, you can see those pylons sticking out on that broad slope to the left there. That is a buried landfill, and those are outgassing points for methane as things are being decomposed under the surface in a more anaerobic environment. And hey, look, these two things match up pretty well. There's the Keeling curve again on the left. And on the right, we see the global monthly mean for methane, CH4. And they match up pretty well. And you might be saying, well, this might just be, standard atmospheric cycles, right? That's one of the big things that a lot of people who deny climate impacts say, oh, this is just, the Earth's going through a cycle. Well, it isn't. It's going through a human cycle. This here is how we extract ice cores from places like Antarctica. Or in this case, this is how would you pronounce this? Quilcaya ice cap in the Peruvian Andes. And these scientists are extracting cores to do something really, really cool. I'm going to provide a video by the Be Smart folks from the PBS Digital Studio to kind of really go into depth on how this works. But for your purposes here today, we extract these ice cores, we bring them back to the lab, and we're looking at these tiny, tiny little bubbles. So through two different things, through being able to count, almost like you do with tree rings, what we call the varves of these ice cores, we can basically figure out, one, how old they are and how old this ice is. And then we can look at these little tiny bubbles. And those bubbles capture basically the state of the atmosphere at the time that it was formed. So as ice falls onto the planet, as snow falls onto the planet, it is buried by more snow. And as that snow starts to condense and those crystals start to break down, they compact and they capture small little bubbles of air. And as they really compact, they squeeze out most of the space, and these little bubbles are what's left. You've probably seen ice and it has these little trapped bubbles in it. Well, we're doing that, but we're looking hundreds of years, if not more, into the past. So here are concentrations of greenhouse gases from the year 0 to the year 2005. So now 2022 years before the present to 17 years before the present, I guess, back in 2005. So this is for carbon dioxide, methane, and nitrous oxide, N2O. So that was where we were in the roughly 1700s, about 280, between 17 and 1800s, right before the start of the Industrial Revolution. And that's where we were in methane, right before the start of the Industrial Revolution. And if you look to the right edge of that graph, you might see a very, very, very sharp increase. You've probably heard and seen about this before, but this kind of puts it in a bit better perspective. We've seen a rapid increase in what prior was just a natural holding level. And all of this corresponds to massive increase in industry and human activity on the surface. So here we can see those varves on the left, what one of these ice cores looks like. And then we can see these scientists on the bottom kind of marking things off. So like I said, it's kind of like tree rings, right? You just count back. And as you count back and you get further and further into the ice record, you get older and older. So this figure here presents results from the Antarctic and an Antarctic ice core, the EPICA Dome 2 ice core, showing the development of temperature in Antarctica and the concentrations of atmospheric greenhouse gases, carbon dioxide in blue, methane in red. So there's a lot to take in here. So that top graph is carbon dioxide, the blue, the middle is temperature anomalies, and so the black line with the red and blue gradation, and the red line on the bottom, that is methane or CH4. Also notice the top graph, the blue graph for carbon dioxide is in parts per million by volume, and the bottom is in parts per billion by volume. So we measure these at different levels relative to how much there should be or is in the atmosphere. So over the past 800,000 years, 800,000 years is how far back this goes. So to the right, modern values are indicated by the arrows. So CO2 concentrations when this graph was produced were at 386 parts per million. That was back in 2009. We are over 400 parts per million now. CH4 concentrations were around 1,790 parts per billion back in 2009. So the temperature record shows the temperature anomaly from the present day all the way back. So the 0 point of that temperature scale is the present day mean annual temperature at the drill site here. Greenhouse gas concentrations, as I said, are given in parts per million and parts per billion, pardon me. And past temperatures and greenhouse gas concentrations are seen to show a strong degree of covariation over the entire period of time, except for now. So this is related to natural variability and glacial cycles. So in a couple of slides here, we're going to see how to identify these different glacial cycles. So in recent times, though, greenhouse gas concentrations are seen to show a very abrupt rise, as I mentioned before, to the natural levels of the past 800,000 years. This rise is caused and marked by mankind's extended use of fossil fuels since the Industrial Revolution. Here we can see, again, we showed this a little bit earlier or something similar, what those levels kind of were at, like the extremes prior to us doing things on the Earth and doing things on the surface. Here we can see the different glacial periods. So how would we identify a glacial period? Well, the kind of dips in methane and in carbon dioxide, there's more being stored and there's not as much available to the atmosphere. So those are the low points in our curves. So the kind of the blue on the temperature and those really big valleys in extreme glacial periods. So when most of the Earth was covered in continental ice sheets. All the way to the right, we can see the most recent one, circa 18,000 years before the present, the Wisconsin glaciation. And then here we can see the interglacial periods as well. So those are kind of marked by a steep rise in methane and carbon dioxide and temperature as well. So there's that relationship between temperature and gas outgassing of these more aerobic and anaerobic conditions. So there's more decomposition on the surface. There's more available water to outgas and release. There's relationships here. And here we can see it all together. So we see these different cycles of glaciation. But then if we look to the right, we see where we are now. So this isn't just a noise on the signal. This is a shift in the signal, if you will. Finally, moving into talking about ozone. So as we kind of mentioned before, there's good and bad ozone. So in the stratosphere, ozone is created primarily by ultraviolet radiation. When high energy ultraviolet rays strike ordinary oxygen molecules, or O2, They split the molecule into two single oxygen atoms known as atomic oxygen. A freed oxygen atom then combines with another oxygen molecule to form the molecule of ozone. There's so much oxygen in our atmosphere that these high energy ultraviolet rays are completely absorbed in the stratosphere. Ozone is extremely valuable since it absorbs a range of ultraviolet energy. So when an ozone molecule absorbs even low energy ultraviolet radiation, it splits into an ordinary oxygen molecule and a free oxygen atom. Usually this free oxygen atom quickly rejoins with an oxygen molecule to form another ozone molecule. Because of this, because of this ozone oxygen cycle, harmful ultraviolet radiation is continuously converted into heat. Natural reactions other than the ozone oxygen cycle described above also affect the concentration of ozone in the stratosphere. Because ozone and free oxygen atoms are highly unstable, they react very easily with nitrogen, hydrogen, chlorine, and bromine compounds that are naturally found in Earth's atmosphere that are released from both land and ocean and marine sources. So for example, single chlorine atoms can convert ozone into oxygen molecules, and this ozone loss balances the production of ozone by high energy ultraviolet rays striking oxygen molecules. So just to kind of show that a bit more visually, here we can see UVA radiation will get through most of the atmosphere and get down to us. UVB is mostly absorbed in the stratospheric ozone layer. And then UVC is completely absorbed by the stratospheric ozone layer. But then once you get down lower, there's surface level ozone, and that is our fault for the most part. There shouldn't be the dense layer of surface ozone, and that is contributed by things like transportation and industry. So there are lots of nitrous oxide and volatile organic compounds that then interact with sunlight and little wind, and you'll get these smog layers over major metropolitan areas. So think of like Beijing or Los Angeles, San Francisco, over in India as well. You get these massive smog layers that will just hang over a city. They really contribute to warming, which is a major concern. They are terrible to breathe in. And it can be a really big sign of a vast pollution issue, which we are dealing with now. So to kind of recap, we talked about permanent gases and variable gases. We talked about particulates, the carbon cycle, relationships between carbon dioxide and methane, and then kind of good and bad ozone. And then on top of that, we kind of talked about how humanity is influencing these trends that we're seeing. And it's definitely not a fun story to hear or a fun story to tell, but this is where we're at in the state of the science and trying to figure out how to improve and rectify a lot of these issues. So I hope you learned a lot from this one. I will be back in the next video talking about Earth-Sun energy balances, and we'll get into solar angles and seasonality. So we will see you in the next video, and I hope you have a great day.